For having me tonight. I hope I don't disappoint too much, especially following what happened last year and how well that was done. So this is actually kind of a hybrid talk that I gave. I gave at USF, or not USF, at SEU. You got me thinking about USF. I gave it SEU last year, and then I went to the theology club and added some more to it. I know I'm supposed to go till 8 o'clock, right?
Yep.
9, 10.
Okay, that's probably a little better. I know that I had 17 slides the last time I gave this presentation, and I realized 45 minutes in I was on slide 11. So I do tend to get a little carried away with jabbering on, so if anybody sees that I'm taking way too long, just yell at me to hurry up or give me like a move it on. Okay? And I guess it's also probably time I should admit that I have this up to now 18 slides. So that's a good another 30 minutes right there with that extra slide. So
We got cookies and coffee. Cookies and coffee.
there you go. Feel free to get up and get them anytime you want. If I'm talking too long and you're falling asleep. I am recording this. Hopefully put this up on YouTube for anybody that didn't get to be here can see it. It'll also probably be a great way if you have insomnia to get yourself to sleep. Go ahead and pull that out. I have other videos on there talking about physics and calculus and stuff as well. Great way to sleep. Okay? So what I wanted to talk about was just, some of my favorite things to talk about, and it's kind of a physicist's view on it. And this is what I went for when I first made this talk up, because I'm the only physicist at Southeastern. And so there's a lot of biologists and chemists, and I thought, well, let's kind of give out what the physicists thought on the philosophies of science, and then it's kind of just grown from there. So let's see if we can get through this in a decent amount of time. So I want to talk about the fundamentals of science, just basically what the ideas behind it are, what models are, and then assumptions. Okay, so these are the kind of things we're going to go through and touch on those three areas as we go through it. So for the foundation of science, we basically have two different types of for science. We have fundamental science and emergent science. I am here to talk about fundamental science. This is like physics, right? This is where we look at the most basic thing we can versus the emergent sciences, which are more like chemistry, which come up out of the fundamental ideas, and you start doing bigger and more grand type things with them. Okay, so I'm not really an expert in the emergent sciences, but I am more of a background in those fundamental ones. And when we're looking at fundamental sciences, what tends to be, at least in my understanding of my view of this, is that the most fundamental thing we can do is look for correlations. All right, we try to look and see if I do one thing and something happens afterwards, does that continue to happen? All right, if I take a glass of vinegar and I dump baking soda into it and it bubbles up, and then I think, oh hey, maybe putting the baking soda in the vinegar made those bubbles. And if I do it again and it bubbles, and I do it again and it bubbles, then I start to build up a correlation, and I start to kind of build a cause and effect type of mentality with it. Okay, you have to be kind of careful with this, because you have to do it enough where you're pretty sure it's not just coincidence. For example, if I were to walk in front of a building and then the building collapsed as I was walking down the street one day, would I then just say, well, okay, I walk in front of buildings and they collapse? Well, no, I'd want to repeat it. Okay, so then maybe I walk in front of the next building and it collapses. Then I'm like, well, there's a little bit of a correlation there. And as I keep doing this, maybe the buildings keep collapsing, And I started thinking, well, yeah, I walk in front of a building and it collapses. But it also might just be that they were demolishing that street that day to build a mall or something, and it was just coincidence. So you kind of have to balance that. In order to, I would say, in order to absolutely prove that my walking in front of a building causes it to collapse, I'd have to absolutely prove where there's no way, 0% chance that it is not that. I'd have to walk in front of every building that has ever been or ever will be and have them collapse, right? And I cannot do that, all right? So it kind of leaves you in that idea that we can get to the point where we're like, yeah, this seems pretty good, but we're never 100% sure on something in science, and we shouldn't be, all right? And it's been, and I might be getting a little ahead of myself on the slides, but it's kind of been one of the things that a lot of scientists have done wrong throughout history is when they've claimed this is a fact, we know this, we're certain of it, and then just a short while later they find out something new that they didn't know before, and you're like, oh, okay, that's all gone. So, you know, we have to be careful about that. So when we observe these correlations, we try to make models for them, all right? So let's imagine I have a box, and I can't open this box, but it has a hole in the top, a hole in the bottom, and I can drop something in it and see what comes out. And so let's say first I drop in a big rock, and then out at the bottom come little rocks. Well, I try to come up with something that could be inside that box that caused that. You know, maybe I come up with, oh, there was, you know, these cross-cutting blades or something like that that cut it up and broke it into little pieces, okay? And so then I think, well, if that's the case, if I drop a chunk of ice in there, I should get, like, you know, broken up ice pieces. But instead, I drop it in there, and instead water comes out the bottom. All right, at that point, I look at it and think, well, my model didn't really work. It worked in the first case, so it was okay, but it didn't really make the correct prediction for the second time. So at that point, I have to do one of two things. I either have to come up with a totally new model, or I have to make an adjustment to the model in order to make it explain what I see. So maybe perhaps now I say, well, I want to keep those blades that are in there that broke up the rocks, but now I want them to be heated. And since they're heated, they melted the water, they melted the ice into water, and that's why I didn't get like crushed ice coming out of the bottom, but rather water. And so then I think, well, if that's correct, I throw a piece of bread in there, I should get little chunks of toasted bread. So I throw a piece of bread in there, and wait, there you go. I got little chunks of toasted bread. Then at that point, I'm like, all right, now my model is working. You do have to be careful with this because if you just keep making corrections to your models, it gets to be a little dangerous. Because then they get more and more complicated, they get to be, you know, and you have more and more trouble with it. So I don't know the answer to this, but at some point, if your models just keep failing and you keep having to make fixes to them and everything like that, I don't know where the point is exactly that you then cut it off and say, all right, I have to make a new model. I got to start over. You know, this one's not working out. And I think historically, scientists have been very reluctant to do that. They get very set in their way on this model is correct, and they'll do just about anything to make sure it still works. And you know, we'll talk about some more of that as we go as well. Okay. Next one is, do models actually describe reality? Okay. So I would say I don't know, and does it really matter? All right, I'm going to give an example that Richard Feynman gave, someone who is way more intelligent than I could ever be. But he was talking about this in the terms of quantum mechanics because it was really bizarre. It still is pretty bizarre, the things that it, you know, says kind of happens. But he said that if we went outside and we looked at the sun setting at the furthest north point that it set, right? And we tracked it and said, oh, it went right down over the top of that mountain over there or something, right? And then we went inside and we had two jars. One jar was full of beans and the other was empty, and we moved one bean over. And every night we went out and looked where the sun set. And every time it didn't set behind that mountain peak, we moved a bean over, okay? And then we kept doing this until it went back and set behind the peak of that mountain again. Now, I could go back in and count up how many beans I moved over. And now I have essentially a model where I can predict when the sun is going to set over that peak. So this is useful, right? It is a model that works. I can repeat it. I can do it again. It's going to come out to be those same number of beans every time. I could go inside and just count beans every day and never look at when it sets over the peak. And then as soon as I get to that number of beans, walk out and say, all right, look, it's setting right where I expected it to. All right? But that doesn't necessarily mean that the sun set location has anything to do with the beans, right? It's just a useful tool, okay? And that's all we really need for them. They help us to do something. If they do, they're useful, we use them. And it's kind of hard to talk about them as So whether or not they really describe reality or not. Okay? So one of the big examples here was that uncertainty principle in quantum mechanics. I'm sure y'all heard of that kind of thing. All that quantum weirdness where, you can have something that goes through two different doors at the same time. And then there's that one famous thing about the cat, right? Schrodinger's cat, which is, I think, come to be used as like this great example of quantum mechanics. But my understanding is that Erwin Schrödinger, when he came up with this as an idea to show how absurd quantum mechanics was. And now it's used to like champion quantum mechanics, like, oh, this is really what happens. So, do you need this to be grounded in reality? No, we just need it to give us good examples. And then you get to something like quantum mechanics where all you have is math. That's really all there is. You have a bunch of math, and then the math tells you, all right, this is what you should expect to see. All the other things that come after that, all the different interpretations, they're just that. They're just interpretations. There's nothing in the math that says, oh yes, there should be a multiverse, or oh yes, this is what this means. All it does is say, hey, if you do this, this is what you're likely to see when this happens. This is what you're likely to measure. So when people say, oh, we have reality is quantum mechanical, I don't know about that. I mean, maybe it is, but it also could just be a very good and useful tool for us, because it actually has been a very successful theory as far as making predictions and being very useful. So here, can science models answer everything? And then some of the things that I've heard said before to me in the past is something like, almost everything is figured out. In fact, I was just having this conversation with someone just a few nights ago when they were asking me, and it was kind of weird, they asked me about the multiverse. And I'll talk more about that later, but I kind of got into that conversation. And I've had others tell me that too. Well, we've got everything figured out. Back in the late 1800s, I believe it was Lord Kelvin said that physics was a dead subject. That there was only two things left in all of physics to figure out, and then we'd know everything. One of them was the consistency of the speed of light. No one could explain that. And the other was something called black body radiation, which was you heat something up and it glows. And we weren't getting the correct predictions about how they would glow. So all we had to do was figure those two things out and we were done. The thing is, the solution for the consistency of speed of light was Einstein's relativity, which was a giant revolution in the way we were thinking of science. And the solution to black body radiation was quantum mechanics. So the dead subject really just kind of blew up. And you look at something and you're like, hey, we've got everything here. Even if you can go along and describe and predict and explain everything that you've seen, you don't know that you're not going to see something new tomorrow. There could be something brand new tomorrow that you've never seen before that suddenly your models and everything don't explain, and you either have to make a correction or you have to start over. And that brings me to my thought of the unknown maze. Okay? This is one, I don't know if it's a great one or not, but it's one that I came up with. It's when I hear scientists say, we have this figured out, we know this, we're certain of this, we've almost got everything figured out, I feel like that's someone who's lost in a maze and they have no idea how big the maze is, but they're certain they're near the end. Right? We've been walking for a while, we haven't hit a dead end really, or too bad of a dead end, and we're certain we're about at the end. Well, you don't know, are you in this maze? Is this maze the size of this camp here? Is it the size of this county? Is it the size of this entire state, the entire planet, the entire solar system, the entire universe? Like, how big is this maze? We have no idea. So you never know what's coming tomorrow. You have to be really careful about saying that we've got this figured out. Okay? And on that same note, is it safe to say we have stuff figured out now? It's safe to say that, we probably had no more than we used to. We seem to have lights and TVs and cell phones and stuff that work. So we have better models that make better predictions. But that doesn't mean we necessarily have it figured out. And then that brings me to the idea of dangers of proven facts. I don't let my students use those words. I don't let them say fact. I don't let them say prove, or this has been proven. I usually am a bit nitpicky about that, and I make them say something like, it has been shown to be consistent with, or things like that, rather than proven. Because when you use that word proven, and you use this is a fact, that is saying there's no doubt. And there's always a doubt. There's no way we are humans. We cannot be 100% certain of anything. And so there are some things that I am pretty certain of, like that our entire planet is a sphere, right? I'm pretty certain of that. I've seen pictures. I've also done the experiment with what is called a Foucault pendulum, and the only way you can explain the motion of it that we know is that we're on a big sphere that's rotating. So I've even done some of the experiments to show that it is. But if someone came up to me and said, I have figured it out, I can explain everything, the earth is flat. I can even explain that Foucault pendulum, I can explain all these pictures. I wouldn't immediately say, nope, you're crazy, get out of here. I'd listen to them. I'd say, all right, tell me. That doesn't mean I'm going to agree with you, but I'm going to listen, right? Because if I don't listen, then I'm not really being scientific. I'm not considering everything. I'm not even questioning my own assumptions and my own thoughts and my own logic on this. So you should always be willing to listen and consider things, but not necessarily agree with them, right? Because maybe they come along and they tell me something, and I'm like, well, no, actually, I think this is incorrect. So you have to be careful about that. And then, of course, the last thing is science doesn't say anything scientists do, all right? Like I was talking about with quantum, it's just math, right? The math doesn't tell us this is the way the universe, it just says this will tell us a prediction about what happens. It's the scientists that put their own predictions on things, all right? So we have to be pretty careful about that. How am I doing here anyway? Not too bad? I'm trying to go fast. I feel like I'm leaving stuff out and just kind of throwing it all out at you as fast as I can, but we're okay? Okay. My wife gave me the thumbs up, so, which by the way, I should thank her. I do not make PowerPoints this pretty. She stepped in and did this for me, so I appreciate this. And then the last time I tried to give this talk, I guess I messed up, but none of the pictures would show up. So it's fixed now. It's a lot prettier than the last time I ever tried to use some of these slides. And then a lot of people think the only thing you can do is, we have to turn to science. Science is the only thing we can get answers for. But there are answers outside of this. And this is an example I got from John Lennox, very bright guy, mathematician, very, very bright. But he was pointing out that you can have answers outside of science. For example, if someone asked you to explain modern cars, you could talk about internal combustion, you could talk about entropy, thermodynamics, all the mechanics of the engines, all that kind of stuff, the torques, all that kind of stuff, and explain a modern car. Or you could talk about Henry Ford and assembly lines, right? Talking about Henry Ford and assembly lines and industrialization, that's not talking about science. That's just talking about what happened. And both are equal explanations of what happened. One is, this is how it works. The other is, this is kind of where it came from. And I feel like that with our universe. We can have things where we say, okay, we see that the universe works this way, but that doesn't mean, we can't also explain it with God. Okay? Yeah, I think what he said was that the designer does nothing to diminish the rules that you've discovered about a system. So just because you had someone design it doesn't mean like you're going with that whole, what say, the God of the gaps thing, which I'm also going to talk about here in a little bit. Okay, assumptions. In some places they're called axioms, in other places they're called postulates. So usually in mathematics they say axioms, and in sciences they say postulates. But essentially, all these are just initial assumptions that you can't prove. All you can do is just say, we believe this is to be true. All right, everything we've done so far shows that gravity pulls things down. I'm going to assume it always does that everywhere in the whole universe, and I'll go from there. But it's still an assumption. If you later on find out that that was not the case, then you've gone down a completely wrong path, and you're in trouble. So there is not a single postulate or axiom-free science or mathematics. Everything starts with an initial assumption. Even math has the axioms that they are built on. And in fact, if you look at something like mathematics, there's literally an infinite number of initial assumptions we could make about mathematics and an infinite number of different mathematics we could come up with. I've been pretty firmly in the camp that we don't have the right assumptions in mathematics. I think there's something wrong in our mathematics, just because so much of what we try to do doesn't quite work out, and we have to just start estimating everything. In fact, if you look in quantum mechanics, there's like a handful of questions that we can answer exactly, and every other solution we come up with has to be an approximation. All right, and it doesn't, there's like continuousness in mathematics where there's a lot of discreteness that we seem to see in reality. So I don't know that it's necessarily the best math to describe our universe that we have so far. That doesn't mean I know a better math to propose to replace it. If I did, I'd totally have published that and be off somewhere else being famous and not here with y'all. So, but no, I don't know what better ideas, but it might be out there. It only takes one person to come along and say, oh, we have to think this slightly bit different, and then suddenly you have that Einstein that comes along, or Newton or something like that just throws everybody for a loop and get that. So yeah, okay. Let's hope this works here now. We ready? I'm gonna try this. Piglet. Are we owl? Is it gonna play? Well, I guess I'm not hooked up to the sound system. I didn't know that.
It's loading.
Is there sound on this TV?
Maybe.
If not, I'll just describe what happens to you.
Can you hum?
Yeah. I'm not gonna sing the song though. So, anyway, in this wonderful clip, I want you to imagine that all of the wonderful animals in the 100-acre wood have found themselves down at the bottom of a pit. Okay? And they're all stuck down there, except for Piglet. Piglet's the only one out there. And they're sitting down in the bottom, and they're telling Piglet to help them. And of course, Piglet can't figure out to help them. And someone says, hey, you need to go get Christopher Robin. Bring him back, and he'll help us, essentially is it. And Piglet is scared to go off in the woods by himself to go get Christopher Robin. So, Owl flies up out of the hole, right? He lands, gives Piglet this wonderful speech. And remember, in this show, Owl is the brilliant one. He's the genius of the 100-acre woods, the one they always turn to for all the answers. Flies up out of the hole, gives Piglet this big impassioned speech about how he can do it and go through this wood fraught with danger and come back and save them all from certain death. And they'll stay there and wait for him for weeks if necessary while he goes on this grand thing to save them. And then he sends Piglet on the way and he flies back down in the hole to wait. And he gets down in the hole and they're all staring at him, with their mouths hung open. And Rabbit looks at him and says, Owl? And he says, what? And he says, I can't believe how wonderful a speech that was. And so the point I'm trying to get to on this one is, how do we know we're not Owl? Right? We look at what Owl did and we're like, oh my gosh, that's ridiculous. The answer was so obvious. But, if you're God looking at us, we're probably lower than Owl, much, much lower than Owl. And we think we're so smart and we don't even see the horrible, glaring flaws in our own reasoning and thinking. Right? It could just all be right there. And then, of course, you're the smartest one in the room and everybody else is like, yeah, I don't see it either. They don't see a problem with it. And then you all just go along with it. But there could be something just right there in your face and we're all just missing it because we're not smart enough. Right? Wonderful video though, huh? You like that?
Oh well.
Yeah.
Try pressing play, just see if that works.
Oh. Yeah, it isn't loading across the bottom. That's why I was waiting for it to. Oh, there it goes.
Minute? My gracious, that's it! Piglet, go to Christopher Robin's house.
Oh, I see. Yes, Piglet. Go and bring some honey.
Yes, bring some honey. Oh, the jump rope, Piglet, the jump rope.
With a little honey on the side.
All by myself.
Yes, Piglet. Through a dark wood fraught with peril, on a mission of life or death, it is a task of great complexity, but I have full confidence that you shall return victorious and rescue us from the abyss. Go forth, Piglet, and we shall await your return, for weeks if necessary. Owl? What? I can't believe how wonderful that speech was.
I can't either.
Move me to tears.
I don't know. I think it was a little better just me describing it. Right? I think I should just take that on out and go with the describing it. But yeah, we may very well be owl. Okay, this brings me to the next part. Can we trust our own thoughts? Okay? If we take the naturalist view, no God, just everything was some sort of random process, right? Why in the world would we trust our thoughts? Would you trust a computer that you just set out for a while and let randomly program itself? I wouldn't trust that that if I gave it some math, it was telling me the correct thing. So why would we trust our brains? Why would we trust our thoughts? How we view anything like that? There would be nothing to trust. Okay? Your brain is just a random thing that has occurred. To me, that means we can't trust our brains, and therefore, if we can't trust our minds, we can't trust any of the logic we're doing, we can't trust anything we're doing, and we're not just maybe owl, we're much worse than owl in that case. However, I tend to go with this second view here. All right? God created us in his image, and he's given us the ability to think. Right? If that is the case, he's given us the ability to think rationally, then we're at least owl. Right? We can at least be somewhat like owl. Not every thought owl has is horrible, right? It's just not always the best ones. So we at least have some rationality here to us, which I don't think there's any way to reason to or even trust that we've reasoned to it correctly if you take a naturalistic view that we can be rational. All right? So that's actually one of the biggest assumptions we make. When I was talking about the postulates and the assumptions in math and science, one of the biggest assumptions we make is that we're rational, that we can trust our own thoughts. And I don't know. If you don't have God, I don't know how you can say that is the case. Next one. Look at this. How far? I'm 34 minutes in and I'm on slide 11, so I'm 10 minutes ahead of where I was last. So, extraordinary claims require extraordinary evidence. Anybody ever heard that one before? I hear that one a lot, right? You make an extraordinary claim. And it's often applied to the existence of God. If God exists, there should be some extraordinary evidence. And I'm not sure that you could do this, even if you wanted to. Because let's imagine, and I've kind of had this talk where I've had a lot of conversations with atheists and a lot of discussions with them. And what I eventually kind of came to realize was that there was absolutely no evidence that would convince them. And so I kind of got into the habit where right from the get-go, or pretty close to it, I would ask them, I'd say, if the skies opened up one day and God came down and said to you, I am real, believe in me. I said, would you then go to church or would you go to the hospital because you think you were going crazy? And almost all of them say, I'd go to the hospital. You know, there is no evidence that they would accept. And let's say we take it even, let's say we take it a little further. I'm going to skip down to 3 here. What if there was some sort of proof? Like, what if God set something down on this planet that we could not explain? Right? It just suddenly was set there. We couldn't move it. We couldn't cut it, we couldn't do anything to it, it was just there, it made no sense, it was just floating there, none of the tests we ever did on it. Well, what would people do? They wouldn't say, oh look, this is proof of God. They'd say, oh, let's figure out a naturalistic explanation of this. And they would try to come up with some model to explain it. So no matter what happens, the people that don't want to believe, they're going to do that. They're going to want to come up with an idea that doesn't require them to have to believe this. All right? So no matter what happens, if you have that extraordinary proof, they're going to try and make it not extraordinary. I think us just being here and having this conversation, that's extraordinary proof. We're just so used to seeing it, we don't realize it as much anymore. The simple fact of the universe existing and how large it is, that is extraordinary proof in my mind. Okay? And then they also don't seem to apply this to some of the pretty wild claims they make in physics, like about multiverses and things like that, where they make these pretty big claims. Dark energy, dark matter. Y'all have heard those terms before? Y'all know what that word dark means in that context? It means we don't know. That's literally all it means. It means we looked out at a galaxy that we expected to be a certain number of years old, and it's not the right shape. It still has spirals going around it. You've seen those spiral galaxies, and we think it shouldn't have spiral arms at this point because it should have spun around so much that you can't see any spirals in it. It should look like a glob. But it still has spirals. But wait a second, that thing has to be billions of years old. But it can't be billions old and have the spirals. So what do? Oh, well, dark matter. Dark matter did it. There's some sort of dark energy, there's some sort of force out there. We don't know what it is, but it's kept it in spirals. Like, well, okay. That to me is a very wild claim. We have no evidence this other than that other than that they need that universe to be billions of years old, or that galaxy to be billions of years old. And it doesn't look old. So we have to come up with something else that makes it, well, that's why it can still look young. There's dark energy, there's dark matter. But again, that's another one of those things I'll talk about in a little bit. Fine structure constant. Anybody ever heard of this thing? This is like the foundation of all the science we have. This thing right here. It's our fine structure constant. You notice here it is a very nice relationship of charge, the permeability of free space, so that's about how strong the electric fields are, Planck's constant, and the speed of light. It's all these fundamental constants that we have discovered separately, and they all hook together, and they come up with this one number. It's about 1 over 137. Not exactly, it keeps going. But it doesn't seem to change. Right? And no one can explain why it has this value. There's no reason why why it would be this value and never be any other value. But if it was a different value, then molecules wouldn't even form. All kinds of stuff would not form. We consider it a constant. It's a fine structure constant. Technically, it's only supposed to be constant now. It's settled on this value. The idea is that it could have been different in the past, but we don't really know how different. Or if it could be different tomorrow, or different next week, or any of those kind of things. And if it did change, or we found that it changed according to location, we'd have to rewrite every type of science that we have. It would undermine all of our dating of materials, ages of things, all of astronomy, paleontology. It's all founded on this thing, right? If this thing changes, all our laws of physics change, all of our dating methods, all of those kind of things all change. We got to start over. So, however, a changing fine structure constant, which there has started to be a little bit of evidence of, could fix a lot of things in science. For example, the universe, as far as we can tell, is in what is called thermal equilibrium. This means that it's all the same temperature everywhere, right? We look out that direction, and we look out 15 billion light years, and we see a certain temperature over there, and we look out that direction, 15 billion light years, and we see a certain temperature, and they're the same. The problem is, according to the model of the Big Bang, those two distant points, they have never been in thermal contact with each other. And they should not be the same temperature. they should be different temperatures, but they're the same temperatures. So in order to keep this idea of, the Big Bang, they come up with this idea of the expansionist theory, where initially the whole universe exploded, and for a very brief, small amount of time at the beginning, stuff could break all the laws of physics, go faster than the speed of light, everything came to thermal equilibrium, and then the laws of physics all kicked in and everything went just as we predicted from that point onward. Now, to me, that's that thing I was talking about where you have a model that doesn't explain something and you just start adding stuff onto it. At what point do you go back and change that? Right? Even with this, and this isn't something I had in here, but even with that James Webb telescope that has come online, they're finding things that aren't matching what the predictions are. They're finding more galaxies out there than they thought there should be. The galaxies look younger and different than they were expecting them to look for how far away they are. So there's some stuff coming up that isn't quite fitting it. But changing the fine structure constant can, in some cases, explain that. You can get things that are that far apart but still in thermal equilibrium, right? By making those changes. And to me, that seems like a simpler thing. This could have been different in the past, and therefore the speed of light was much faster in the past, and therefore they could have come to thermal equilibrium in a much smaller amount of time over a further distance than we've allowed for. So, yeah, I don't know what's more complicated, that expansionist theory where it just magically changed rules, or something that was more consistent and slow change and we're like on an asymptote of it or something. Okay? This one I like. They always like to say that God of the gaps. Oh, you're just explaining that. God did it, right? Well, again, quote John Lennox, I don't believe in a God of the gaps. I believe in a God of the whole thing, right? But I'm not sure that they've ever noticed that they do the same thing. They do that with something like the multiverse. Because in quantum mechanics, one of the big problems is you set up a whole bunch of particles that are all exactly identical. Set them up the exact same way. And then you go and measure each one of them, and they're all different. They all end up at a different location, even though you set them up the same. If I went out and dug 10 holes and put a basketball in the center of the bottom of each of those holes, all the same depth, and every hole I look in, the basketball is going to be right in the center. I dug them exactly the same. That doesn't happen in quantum. In quantum, I dig 10 holes, I put the basketball in there, and then every one I look in, the basketball is doing something different. Even though I put them in the exact same way, and the exact same type of hole, and everything like that, it's different. And that's what leads to that uncertainty principle, that we can make a measurement, and then we see something. Now, originally, the idea was that you had this fuzzied out view before you make a measurement. The particle, that you're looking for, this basketball, could be here or there or wherever, and then you make a measurement and it chooses one of the places to be in. Until people started pointing out, well then who's making that choice, right? It sounded like a choice. So the creationists jumped on that. So then they started coming up with this idea of multiverses, where they said, no, what happens is you make a measurement and every possible outcome occurs, and each outcome that occurs just makes its own universe where that outcome has occurred. Okay, they usually give an example of something that's 50-50, like I flip a coin and it comes up heads, or it can come up tails. Well, when I do that, one universe is created where it came up heads and one is created where it came up tails. They always do it with 50-50. I've yet to find anybody that can explain to me when it's something like 70-30. When the odds are that, do I get like 7 universes where it was heads up and 3 where it was, tails up, or 0.7 universes where it was heads up, or 700 where it was heads up and 300 where it was tails? Like, I don't quite get that, because most things in quantum mechanics are more than just that little two-state, one or the other. There's a whole lot of possible outcomes, and they all have different probabilities. So I don't know. I don't quite kind of buy it. That feels like a multiverse of the gaps. We can't explain that, so multiverses. Oh, dark matter. Oh, dark energy. Let's just throw those in there, fill in those gaps. So it's quite a lot of at least it appears to me, a lot of accusing of creationists for doing the same thing. They're saying you're doing this, but they're doing it themselves. Oh, I think I just added this one today. This was my extra slide. That doesn't mean we're at the end though. I put it somewhere in the middle, okay? This one I like, and I was thinking about this one is you hear them say that a lot, and some of the most famous scientists, they would be asking, where's God in all of this? Oh, we don't need God to explain this. You hear that from a lot, like Stephen Hawking said, all we need is a law of gravity. We don't need this, we don't need God, we don't need these things. But logically to me, that doesn't mean that gets rid of God. If I walk out into the woods and I find, a bunch of charred remains where there was a forest fire, I could say, yeah, I can explain that totally naturally. It was dry and lightning struck and started a fire. That doesn't mean, though, that it couldn't have been a person who came along and threw a cigarette out a window and started the fire. Right? Doesn't mean someone didn't come along and use a match and start the fire, or a magnifying glass. Like, just because you have one explanation doesn't mean it can't be the other ones. And one of the things they often talk about in science where they say, oh, the simplest answer, that's the right one. You really shouldn't say that. Maybe it's the best one you should kind of go with, the simplest one. But the simplest explanation just because it's simpler doesn't mean it's right. There could have been some big thing where people are out in the woods having some crazy, fireworks fight with each other with bottle rockets and started the fire. That's kind of a complicated situation compared to just a lightning strike, but just because you have something simpler, a lightning strike, doesn't get rid of it and say, well, those other things couldn't have possibly happened. I don't need them to explain the forest fire. Especially when you have limited knowledge about a situation, which, as we've talked about so far, we always have limited knowledge about things. So, yeah, I like that one. Then the next part is, what does it mean to have faith? I hear a lot of these come from atheists. Oh, you have faith. That's believing something without evidence. That's not the kind of faith I have. And I don't think that's the kind of faith we're asked to have. Right? That's not Christian faith. Christian faith, we are supposed to think about things. We are supposed to love with our whole mind. We're supposed to love God that way. He wants us to think. Jesus didn't come and just give us things. He gave us parables, things we were supposed to think about and figure out. Right? It wasn't all just hey, you're just going to do this and just believe it with absolutely no evidence. I mean, even Jesus would say that I did this so that they would believe, and I came here and did this for that. So this idea that faith means you have to do it without evidence, and I don't want to buy that. I don't think I have faith in anything without evidence. So, and besides, as far as Christianity goes, you can have multiple types of evidence. There doesn't have to just be that scientific evidence. People always want there to just be scientific evidence, or they say there's no evidence of something. But there is evidence. The Bible itself is evidence. We have evidence dragons existed. Whether or not you think it's good evidence or not, I don't know. But people wrote about it and said there were fire-breathing dragons. That's evidence. Is it good evidence? I don't know. That's kind of up to the individual, I guess, to decide if it's good enough evidence for you to believe it. But there is evidence. And as far as Christianity goes, I mean, we have historical evidence of it. We have philosophical evidence of it. If you've read, C.S. Lewis and stuff, he has a lot of it in there, where you can get to, almost all of Christianity just by, what would be the nature of God that would make us like this. And I feel like you can reason your way to almost everything that we have just from that. Okay, so even to me, Christianity makes logical sense. I can't imagine if I was God, that there's any other way that it could be done than the way it is done. So, and I can talk more about that too. I can talk more about any of this, but so why do I have faith? Well, I have two big reasons. My personal experience with God. Unfortunately, I can only tell you that one, which usually is just anecdotal and not the greatest kind of evidence for me to just say I felt something. So I don't usually put that forth as the best evidence. But the philosophical and scientific evidence for me is what does it. Right? This is what really gets that for me. Consciousness, my own free will, these are the kinds of things that I don't think we can ever explain naturalistically. I think it was Erwin Schrödinger that said that he could see life being an accident, but not consciousness. Right? We can't even really say what consciousness is, but I do know that I am conscious, and I know of no physical law that, or could even imagine such a physical law that would allow me to be conscious in this, and be purely nothing but what is in this universe. There has to be something external to it. I've never been able to come up with anything that would allow me to say, I mean, I could probably explain everybody else in this room's behavior with a complicated enough machine, right? I make a complicated enough program that I can sit there and have conversations with it. It might even be able to fool someone into thinking they're having conversations with a real person. You play a video game and something bad happens, and the people in the game, all the little pretend people, they react much the way normal people would, but that doesn't make them conscious. But I do know that I am, and I believe that all of you are. And I'm pretty sure you all know that you are conscious, so that to me right there is a huge amount of evidence right there. Something that I just cannot, I can't get past. Okay? Other things is we have organization. So in science, we often want to do things like I was talking about with correlations. We say we see this, and we see this a bunch of times, and it kind of works. And so if you're walking along one day in the woods, and you find a bowl, right? A nice, pretty bowl. And there's no people around, you think, oh wow, look at this bowl that appeared naturally in the woods. No, you think there must have been someone here who made this bowl. And you think that because that bowl is an organizational structure. And everything you've ever seen come into existence that was an organizational structure had a mind behind it. A chair you've seen made, a mind in it. It wasn't just randomly fell together with some rocks or something, right? Like, they had a mind behind it to make that purpose to it and organize it. So we do that when it comes to something like that, but then we look at the universe as a whole and we see that it's organized and it has rules and it has a structure to it. And then a lot of people say, well, no, that's just natural. To me, that's changing the game there. That's saying, all right, I have this goalpost for this over here, but this goalpost for me over here. Double standards. I don't go along with that one. So, and then another part, and I don't know how great this is, but my background is in a lot of computer stuff and programming. And I guess one of the ways I've often thought about this is if you were the last person in the world, but you were an amazing programmer, and you're like, I'm lonely, and you programmed yourself some friends, okay? And they knew who you are, they knew your God, they knew you were right there. How many of them would dislike you? Would any of them? Knowing that you could delete them, knowing no, they would all do whatever you wanted. So it's kind of like that whole thing where like the rich guy comes and he's like, how do I know if she loves me for my money or not? Like those old stories. So they pretend to be poor or something like that to see, how much you really feel about me. If you were going to make computer programs and you really, really, really wanted to have the ones that loved you for you and not just because of what you could do to them, wouldn't you set it up in a way where they didn't really have 100% evidence that you were there and see which ones chose to love you back and which one chose not to? I always feel like that's the situation we're in. We're here to choose, right? I can't stand up here. I don't know of any proof to prove to you God exists, but I sure believe it. And it sure fits the way reasonably what I was saying, like Christianity fits reasonably. That seems logical. It seems like the thing to do. So, anyway, that was my little thought on that, just because I always think about things in terms of programming. So, then this one. Why does God intervene in some instances and not others? We've heard this one before. Well, I think he intervenes in every situation, because without him, none of the situations would occur. Right? So he does intervene in every situation. The question is, why does he intervene differently in some situations than the other? Well, if he intervened differently in every situation, like never let anybody die, then we would just say that's just the way the universe works, and you'd be asking some other question, well, why doesn't he do this different? Okay? So any type of thing where God does things consistently only to occasionally interject and change things to show you he's there, that to me is more proof of God. If God rose people back from the dead, all the time, we just come up with rules of, biological rules to say, this is, people just come back to life. Instead, it's a very rare thing, right, that Jesus could do, and that's it. If it happened all the time, like you can't repeat that experiment. If you repeat it, it's not a miracle anymore. It's just the normal thing, and you write your rules of the universe to match it. Oh, and then and if you're the creator, you can break whatever rules you want, when you want. And the example I want to give of this is a little mobile video game that I made once. And I tested it and had the little highest score. It kept global high scores. So whoever played it, it would compare. And I sent it to my cousin, who's an engineer, and we always argue back and forth who's more intelligent, the physicists or the engineers. I don't have to tell you, it's definitely the physicists. But I sent him the game, and I was like, can you test this for me and try it out? And he sent it back to me having beaten my high score. He's like, oh, ha, ha, I'm the high score. So I thought, well, I don't have time to sit here and get into this with him. So I just went in and changed the rule of the code real quick for my own personal one, where there were no obstacles in my way, and I could basically run indefinitely, and I just let it go until I beat his score, let it update online, and I was like, there you go. And then he apparently went back in and tried really hard to beat my high score, and then he beat it, and so then I just did it again. And I know it's horrible, but it's my cousin, so I think it's okay to tease him like this. He still doesn't know that I did this, so if he ever sees this, he's going to know that I did it. But yeah, every time, and then I think one time he was like, I stayed up all night and I finally beat your high score, and I was like, ooh, I'll just let you have it now at this point. I didn't know you were going to go quite that far with it. But he was my older cousin. He picked on me a lot growing up, so I figured it was fair. But yeah, I mean, I can break whatever rules when I want, as long as I have a reason for doing it, right? If I made that video game and I want to break the rules of it, and I made it, I can do it when I want, where I want, how I want. It doesn't mean I have to break the rules that I made for the video game every single time for every person playing it or anything like that. Although I'm fairly certain God's reasonings for breaking the rules, and interjecting into our universe is much more noble than mine were for editing that game like that. But okay, and then we've made it. Look at that, 7:58. Leave you with this wonderful quote. I really like this one. And I think he would change this now if he was around still, because it says, no amount of experimentation can ever prove me right. And a single experiment can prove me wrong. And I think he might adjust that a little bit, because not everything that gets disproven stays disproven. And a big example of this is Einstein's cosmological constant. So when Einstein wrote his theories, he felt there should be this anti-gravitational force that was prevalent throughout the entire universe. But Hubble came along and showed that this was not the case. The universe was expanding. And Einstein took it out of his theory, called it his greatest blunder, basically apologized for it. And about 80 years after he died, they started finding evidence of this force as they got better telescopes and looked further out. And it started to look like he was actually right. So even something that gets disproven doesn't stay disproven. All right? I think that was it. So. Hopefully I gave you something to think about. I by no means say that I have everything figured out. I hope the big thing you're getting from this is, if you're looking at things scientific, you're looking at all these things, be open to it, be willing to think about it, and don't just accept what everybody else tells you. Think, use your reason, use your logic. You have a mind, it was given to you for a reason, okay? And if you have something that I said wrong here, please tell me, because if I'm wrong, I want to know. You know, you gotta tell me so that I don't get up and say it again and embarrass myself again, so feel free to tell me. So are there any questions, anything? Yes, sir.
When you speak of quantum mechanics, is that related to the quantum computer technology?
It is.
And do you have a handle on where that is today?
Not very far. It's, I don't think it's as far as people make it out to be. Like, as far as like how that technology is going.
Yes.
It's still very much in its infancy. I think the idea behind it, as far as how you can use it to store and compute information in theory is just fine, and it seems to work. The problem is doing it in practicality. So what you're relying on there when you do quantum computing is something called entanglement, where, let's say I do an experiment where I know that when I do this, it's gonna make, you know, one thing that's up and one thing that's down. And I can look at this thing over here and I know that it's up, so therefore I know this one must be down. They are considered entangled, okay? Knowing one tells you the other, and if this one had been down, then this one would have to be up, like that. And so it bases on that. But the problem is, as this one goes off and say it was up, something could change it to down, which wouldn't affect this one over here, because now it's entangled with something else. And so very quickly in quantum mechanics, you have two things that are entangled. That entanglement gets lost very quickly, which means we've lost that information. And that's actually the modern way we think of what entropy is. It's information that gets hidden from us because things get so complex and so intertwined that we can no longer pick out what the original states were. And that seems to be the biggest issue with quantum computers, is you have to keep them cold enough and isolated enough so that the information that you encode in there, that you're gonna then read out, doesn't get lost due to entropy. And that's very, very hard to do. So you have these huge giant quantum computers and you can keep like this tiny little bit of it isolated and get a tiny little bit of information, and you like, okay, I added like 4 + 5 and I got 9, it was a success. But then I lost the information, and now, you know, it was very brief and it was very quick. That tends to be the kind of problem with that. Is that what you were asking about?
Yes.
Yeah.
So it's not practical today.
Not yet.
Do you see that it will be?
I don't know.
Your lifetime.
I had
There are
my
some companies that are working on it.
oh yeah. And if I were them, I would be too. I had my quantum mechanics 2 professor in grad school was working on quantum computing. He'd be much better off at answering that question than me. But yeah, that's about the most I know about that one, is that it's very hard and some very, very bright people are working on it. And I think it would be neat if they figured it out. It would kind of really quickly make all our other computers obsolete, because they'd be so much better than, you know, in theory, what ours can do now. Yes, sir.
Could we ask you to stay for a few minutes for
Sure.
those that have questions? Would that be all right with everyone? Our time is up, and we value your time. We value